Next section in the chapter is flow around spheres and cylinders. So what you're looking at is basically, this picture is the wake behind the flow. So the flow come like this, and then what make it separate? You could think about this basically just like, if one expects, if the flow is actually over a bluff disk like this, the flow will have to separate here, right? Because the flow here cannot just turn 90 degrees. This will not happen. The flow will just come to the edge, and he will just basically have to keep going. Imagine if you are running into the classroom, and then you're supposed to, once you come into the classroom, you're supposed to turn immediately to the left. It will not happen. You just have to keep going a little bit and then start turning. So because of this, the flow will separate from fluff body. All right? So you can explain this in inertia, but later also, if you take another fluid mechanics course, after you fluid one, you will study this in detail, and you will know where this point will actually exist. All right? The point where the flow will decide that I cannot keep going. I will just have to leave. Right? And it has to do really with the pressure in front of it. The pressure here will just be too high, and he will say, I cannot go this route. This is very high. I'll just go this way. So solving the pressure field will tell you exactly where this point is. But what happens is, it's basically the velocity is getting smaller and smaller. I'm not reading the velocity profile. Okay? So you can see how the velocity profile is very thin. It gets thinner and thinner because of it's a boundary layer to start with. And on top of that, I'm telling you there is pressure. We call it adverse pressure gradient. When you're going this way, down the hill, kind of, the pressure actually increases. Why? It's when you go into a nozzle, what do you expect the velocity to do? The velocity will increase, and according to Bernoulli, if the velocity increases, the pressure will decrease. The energy is conserved, basically. So if P over rho is basically related to V square. If you make the velocity increase because the area is getting smaller and smaller, who's paying? The pressure will be paid. Pressure over P over rho will actually end up dropping. So that's why we call this a nozzle, because it speeds the flow, reduce the pressure. You could think of the opposite as a diffuser. So when you go in an area that's getting bigger like this, what will happen? Excellent. The opposite, exactly. The velocity will increase, and the velocity will decrease, and the pressure will increase. So basically, the flow going into something like this keep building pressure. Pressure is getting higher and higher. So now if we look at this cylinder as two parts, this part is as if, and so really it's as if it's going through, what is that? This part? Nozzle. And as a result, the velocity here, one should expect the velocity here to be much bigger than U infinity. The velocity here at this place is almost like twice as large as the free stream velocity. So if the air is coming at 10 meters per second, here it will be 20. The pressure will end up being lower than B infinity. Okay? But then in this part, now it's a diffuser, and the velocity is decreasing and the pressure is building up. So if the pressure builds up very quickly, the flow will say, I'm not going to decrease my velocity. It's very hard for the flow to go against that pressure. Right? And so he will decide that, no, it's easier to go this way. Let's just go this way and leave this place where the pressure is supposed to build up. So that's why you cannot send the flow in any diffuser. You have to stick to a small angle. If you make the angle really big, the flow will separate and will not go to the diffuser. Will not follow the prescription. He will not decrease its velocity that much. He will not increase the pressure that much. So I can send the flow in any nozzle I want. I can make the area drop 10 times into each nozzle. I can make the velocity speed up like crazy and the pressure drop like crazy. But I cannot make the reverse on a diffuser. Meaning, I can send the flow into a small diffuser, small angle, but if I try to make the diffuser bigger, the flow will not go through. He will separate. So as a result, the same pressure ratio from 10 bar to 1 bar, I can make it in 3 nozzle plates because I can squeeze them through a huge area reduction and finish the whole 10 bar into 3 plates. But in the compressor side, I cannot make him go from 1 to 10 bar immediately. I have to be very patient. I have to make the area really, really slow. The area change across the diffuser cannot be huge. So as a result, the flow in a nozzle, the flow always follow you, but in a diffuser, the flow will not follow you if you are greedy and you try to make him go bigger, area-wise. So as a result, the flow will never separate on the upstream side because this is a nozzle. You squeeze him as much as you want and he will go through. He doesn't have a choice, right? Where else he will go? He will have to follow this cylinder. But once you open it here, now he has a choice. He can either follow you and make his pressure go up, or if this area is really, really big, he will say, I'm not going this way, I'm just going straight. I will separate from the wall because you are asking me to increase my pressure really big. Right? And it's that difficulty in building the compressor. That's why the jet engine actually were invented on paper for a very long time, but they couldn't really make them work until the Second World War, where they managed to actually make it really work on the compressor side. Right? Because it's very hard to make the air go without separation. Right? So you kind of understand now why the flow separates. Right? Because the pressure is in front of him is killing him. It's killing those boundary layer. Let's look at this boundary layer. So that boundary layer profile, the pressure basically, the higher and higher pressure that it has to go through once it's crossed this point and start going downhill, will reduce the velocity near the wall. Eventually, reverse the velocity. The flow get reversed, or basically have separated flow. So the flow will go the other way. Right? So once you cross this point, this separation point of flow go like this, there will be actually separated flow like this. All right? How can we prevent this from happening so soon? How can we convince the flow to keep going even more before he separates? If only we can boost this kinetic energy near the wall. If only we can make our velocity profile a little bit stronger, have more momentum into it. So what can make the velocity profile more full near the wall? So what I'm saying is that I don't like this velocity profile. I wish I could have it like this. See, you have more kinetic energy near the wall. Excellent. Or basically make the flow turbulent. So amazingly, if you make the flow turbulent over a sphere or a cylinder, his velocity profile will be more full. He will have more kinetic energy near the wall. He will not separate here. He will be able to persist even longer. And so why this is a good thing? Because now the flow is covered by fluid from both sides, a lot bigger area, and the wake region is smaller. So the drag, that's mainly pressure drag, will actually end up being smaller now. So that's why they make the golf ball with all those dimples, because they wanted to make the boundary layer become turbulent. So even someone with a very weak, head, and he cannot make his ball go farther away, they help him by making it turbulent. So even at very small velocity, his Reynolds number is 5 10 to the power 5. Effectively, it's as if it's really not that big. So what they do is that they make the flow transition to turbulence earlier. All right? So this will happen here. See, this what over here, that's the transition from laminar to turbulent. All right? And it happened around, just like a flow over a flat plate, around the 2 to the power 5 or the 5 to 10 to the power 5. It's in that region. So we call this the drag. What would you call it if you have a choice? No, this region or this phenomena, we call it the drag crisis. The drag is going through a crisis. Of course, for us, it's great. I mean, that's basically the golfer happy hour, kind of. So basically what happened is, suddenly the wake is, because it becomes turbulent, the wake becomes smaller and the CD drop from you. This, we are plotting the CD. This is the resistance to the ball. This is the drag force on the ball or the cylinder. This is for a cylinder. This is for a sphere. So they basically almost the same. It's the same physics, whether it's 2D or 3D. Right? Okay, more in fluid mechanics, but that's what happened between laminar and turbulent wake. And so what happened over here, that's the very viscous flow. This is for very small Reynolds number. If the Reynolds number is that small, like 10 and 1 and 0.1, that's basically you are throwing a cylinder into honey. And the flow is very, very viscous. Right? There is no wake. As a matter of fact, in this region, the flow will look like this. Look at this. The flow is basically just sticking to the wall all over it. And so this is basically mainly skin friction drag. There is no wake, there is no pressure drag. Right? Here he's basically showing us by experiments the difference between laminar and turbulent boundary layer. So laminar boundary layer, the flow separate here. The turbulent boundary layer, I don't know whether you can see. The turbulent boundary layer, the flow separate further down. So you see how the wake is actually smaller than this one? Right? So the same idea behind those cars, you know, they try to make the flow separate much longer or much farther. So they would love to make the flow remain attached to the flow as, or the body as much as far as they can, because they don't want the wake to be really big. Right? So if you look at a lot of cars, you actually, near new cars, you will see that they always try to do this, to keep it going farther and farther so that it wouldn't separate. And that's the golf ball, and look at this. If it's a smooth, this is again the CD as function of the Reynolds number, and we expect that transition to happen around the 2 to the power 5, 3 to the power 5, in this range. But as you make the pipe, or sorry, the sphere more rough, that transition happened earlier. So someone with only 4 to the power 4, 4 times 10 to the power 4 Reynolds number, so that's a very weak shock, he will still be able to have smaller drag on his wall. Not because he's moving at higher Reynolds number, but it's because the flow is turbulent, is made turbulent for him because of all those guys.
So without the dips in it,
you will go with this. Without the steps, basically, you will end up transitioning over here. So if your sphere is actually flying at that Reynolds number, you will have this large drag. And so with large drag, you will just have more resistance. So your ball will slow down very quick. Now, of course, if you are really strong and you will end up kicking it, even a smooth sphere, that fast, you will have the small drag. All right? Very good. And more about this in the float course, right? But for now, the heat transfer, because the boundary layer, so I just explained to you that the velocity profile is changing from the leading edge till the point with maximum velocity till the trailing edge, right? The velocity profile is getting thinner and then separating, and so do you expect the heat transfer to be the same all over the sphere or different from one point to the other? The heat transfer, the Nusselt number, do you expect the Nusselt number to be constant all over the sphere, same number everywhere, or different location will have different Nusselt number? Of course, because the graph say, right? I mean, you look at this, there is a Nusselt number, but why? The question is why? So why the Nusselt number is changing from theta equals 0, so that's the leading edge, to theta equal 160, that's somewhere at the back. Why does the Nusselt number change? Or basically, why does the H change? Why the heat transfer? Because H is really a measure of the Q, right? Q is H, A delta T. So why does the H change as we are going across the sphere? Because
the wind hits one side more than the other.
So this, by the way, is this is like going on the upper side only, and the lower side, that's mirror image. He's just plotting it from the top. So what are you saying, Mali? Are you saying that the right and the left have different velocity? Or the upstream and downstream, they have different velocity? Is that what you're saying?
Well, the center on both sides, I mean, that's getting direct wind, and it's going to be turbulent nonsense on the right side of it.
So it's because the velocity profile is different, right? The velocity profile here probably will be more full than this one, which is reversed. It's completely different velocity profile, and the temperature, if we plot the temperature profile, it will be completely different from one place to the other. And this thing is evolving as we are moving across from 0 until 90 until 130. The velocity is changing, the temperature profile is changing, and that's why you should expect the local H to be different, right? Completely different temperatures. But what we care is the heat transfer at the end of the day. How much does this tank lose? All right? So here is the relation for the flow over a sphere. So Nusselt sphere, H d over K. So the Nusselt number will always be H multiplied by a length scale divided by K. That length scale would be the diameter for a cylinder or a sphere. It would be the length of a flat plate. If we have a bunch of cylinders, we will have to check what will happen for us. But there will always be a length scale over here. All right? And that too, that's if you kill down the Newton's number. So you kill the Newton's number, you make it 0, and you'll get the Newton's number equal to 2. All right? All right, so here is the relation. And mu infinity and mu s, this correlation, so this is an experimental correlation because you just realize now how complicated that flow is. So this experimental correlation is done to also take into account if the surface is a different temperature, very high temperature difference between mu s and mu infinity. So everything is evaluated at the film temperature, right? No, actually this one, the flow properties are evaluated at the free stream temperature except for mu s, which is evaluated at the surface temperature. Okay? So let's solve a problem about this. So again, this was in an exam problem. There is this tank, and this tank has liquid nitrogen in it. So they use liquid nitrogen for cooling because at atmospheric pressure it will be sitting at minus 196. So if you want things to be a little bit cold, you basically surround them with liquid nitrogen. And so if the nitrogen is like this, and he's boiling, of course, now, becoming vapor, he will keep at minus 196 all the way until it's all basically vapor, and then he will leave. So if you have your experiment nearby here, it will enjoy minus 196 for a very long time until you basically finish it. So I remember at one summer I was working in Wright-Patterson Air Force Base, and every time we go to the lab, there is this huge army truck filled with nitrogen cylinder, but very long nitrogen cylinder, all the way from this wall to the other wall, because you need nitrogen for cooling. So it's really nice actually to have. And so that's what this problem starts with. He explained to us that the nitrogen in a tank will remain constant at minus 196 until it's depleted. And any heat transfer to the tank, and there will be heat transfer because it's really cold, and the air basically here is at 20 degree. So one should expect the Q to go from the T air, T infinity, to the tank. So he said any heat transfer to the tank will result in evaporation of some liquid nitrogen, which has a heat of evaporation of 198. So the latent heat is, or let's call it HIF, 198 kilojoule per kilogram. All right. So what does it mean? It means that to make 1 kilogram turn from liquid to gas or from liquid to vapor, you need to give them 198 kilojoule. Every 198 kilojoule go into the liquid, 1 kilogram will turn from liquid to vapor. Right? And you give us the density, 810 kilogram per meter cube. And consider a 4 meter diameter spherical tank. So this tank is 4 meters. That's the diameter. And it was initially filled with liquid nitrogen. The tank is exposed to 20-degree ambient air and 55 kilometer per hour wind. So the wind is basically blowing that air on the sphere. All right. The temperature of sand shell metallic spherical tank is observed to be almost at the same temperature of the nitrogen inside. So because the tank is really very thin, and say it's made out of metal, if the temperature here is Ts, the temperature here also is Ts. How come? Well, the conductivity is pretty good, and therefore the resistance to conductivity, or if you remember, it was R2 minus R1 over 4 pi K for a sphere, it's really tiny. So the temperature is almost the same from both sides. All right? So of course he doesn't like this, because then he will make the nitrogen boil immediately and he will lose all the temperature, low temperature he would like to keep. So he would like to keep this tank sitting at this temperature so that he can dump his experiment into this tank and basically enjoy the minus 196 for a very long time. So what can he do to reduce or elongate the time where this nitrogen remain there in the tank? What would you do? You are the engineer responsible for making this experiments last for 5 hours. How can you do it? You have to, right, you have to insulate the sphere. And so he said he will insulate that sphere with fiberglass, 5 centimeters thick, 5 centimeters thick fiberglass, and he give you the K. And of course the K for the fiberglass should be very, very small, so that the resistance become very, very big and take forever. All right. So he would like to find out the rate of evaporation of liquid nitrogen, kilogram per second. He would like to figure out how long, or basically the m dot nitrogen evaporation, kilogram per second. How many kilogram he will lose every second? How do you solve this problem? This is what's required. Solution. And as I always say, you will probably understand the solution when I write it, because I'm going to write 2 equations, right? You know the 2 equations that I'm going to write, and we get the solution. So that's not that difficult to understand. You will get it. But what you need to focus on right now is why we are going to come up with that solution. That's what's really important. That's what you are going to carry to other problems. So it's the first few statements that we are going to say right now, not the detail of which equation we are going to use.
We want to find out our Q dot. That way we know how much energy is being transferred through the insulation to the liquid nitrogen, and then we can use our kilojoules per kilogram and know how long it will last.
Excellent. Excellent. That is the solution, really. So we need to find out the Q dot. We need to find out how much heat is going into that nitrogen, because that many joule per second can be converted to how much kilogram per second will evaporate. Because for every joule per second coming, actually for every joule, you know how much kilogram is going to evaporate. What's the conversion? The latent heat, that 198 kilojoule per kilogram. So if you can tell me how much kilogram, how much joule per second are going into this tank, I will say that Q dot, so you actually, the solution should start from the end. You could just basically say that the Q dot is really the M dot multiplied by that latent heat. Right? This is given, this is what we are trying to calculate, so we better calculate the Q dot. Now it's a heat transfer problem. You have a tank and you are trying to figure out how much Q dot is going through this tank. That's chapter 2, the first thing that we had. If you have a, forget that it's spherical for now, just a tank, and you would like to find out how much Q, what is the equation for the Q? I would call it delta T over R. Let's say that the Q dot is for any wall, you know, spherical, cylindrical, plane wall, the Q dot or the heat transfer is simply delta T over the R, sigma R, all the R's. How many R's we have? Theoretically speaking, we have 4 R's. Convection on the outside, that's the chapter that we are studying right now. We have to go, and because that's external flow, right? Air blowing on a cylinder, sorry, air blowing on a sphere. So we just have to open the section with deal with spheres and figure out if this equation that we can grab from there is working or not. Right? That's external convection. And then you had insulation, that's a conduction through the insulation, and you have conduction through the metallic shell. But that metallic shell, we were never given its K, we were never given its thickness, and he said the temperature is almost the same across it, so let's forget about this conduction through the metallic shell. It's very tiny resistance. And then on the inside, and so that inside also, he said the temperature of the shell is the same as the temperature of the nitrogen. So that basically tells you that there is not really that thermal resistance between the nitrogen and the shell. There is no convection between the two of them. It's not like nitrogen is flowing in a pipe and therefore the pipe will not get its temperature. It will be a little bit different. No, this nitrogen has been sitting there forever in this shell, and so there is no convection inside. Right? So really there are two resistances then. That's insulation and the external convection. Right? So for the, we could actually just write them too here. So the delta T would be the T infinity minus T tank or TS, and the resistance for convection is 1 over H. Let's call it H out area S, or area out actually. We cancel this. So H out, area out, plus the insulation spherical wall, and that was R2 minus R1 over 4 pi K R1 R2. Right? We are almost there now. So we need this Q dot so that we can bring it here in this equation. I know T infinity, I know TS, R2 and R1 and 4 pi K, that we got the resistance of the spherical shell. So what's the only thing that we don't know? H out. External convection. What do? We open the chapter for external convection, which is, where is it? Here, and then I look for flow over a sphere. Well, here is the equation. The 2 to the power 4, sorry, 2 plus 0.4. This one, right? I can cut and paste this. You guys, you'll just have to copy it yourself. I can't copy, why? Something is clicking with me. Well, maybe I have to type it, that's okay. Alright, so I will just say that to get my H, I need my Nusselt. To get my Nusselt, I need to bring the correlation for a sphere. And so that Nusselt was 2 plus 0.4 multiplied by the Reynolds to power 0.5 plus 0.06 196 minus to power 2 over 3 multiplied by the parental to power 0.4 mu infinity over mu s to power 1/4. Is this correct? Yes. And he said that all the properties were evaluated at T infinity except for mu s that's evaluated at Ts. So I will just have to open the tables and get the air properties. So air properties at T infinity. This is the flow around a spherical tank, and in this formula all properties are at T infinity. Not the minus 196, it's basically at, and actually as a matter of fact I don't really know the Ts, right? Do I know the Ts? This would be the Ts for that convection problem. For that convection problem you are dealing with T infinity 20 and T outer surface that we don't really know. It's not the inside temperature at 196. So what we're going to do. Right, so let's get the stuff at T infinity first. So at T infinity, at T infinity you can get mu is 1.51 10 to minus 5 meters square per second. You can get the K. We talked about why do we need the K, right? Because the Nusselt number 254 watt per meter Kelvin. You get the Prandtl because it's in the equation. It will always be there, 0.7309, and you get mu infinity because that ratio you need mu infinity and mu s. 1.8 to 10 to minus 5, and that viscosity I told you it's Pascal second, but another way to write it rather than Pascal second, you could also say it's kilogram per meter second. It's the same thing. Pascal second is the same as kilogram per meter second. And you get mu s, which is also for air, but it's just at different temperature, 1.89 10 to minus 5 kilogram per meter second. All right. So actually, one of you should jump on me right now and tell me what? Say that again. What do you mean? Right, so mu s should be at a temperature that I don't really know. Right, I don't know the surface temperature yet, actually. Right? So, in this exam problem, he gave you mu s. He said, let's use this mu s. If this was a homework problem and you actually have to get this accurately, what should you do? We don't know that temperature, right? But we need that temperature to use that formula. So what's the way out of this problem? Anyone?
Asking for help.
Well, what would I say? What do you think my answer would be? Say that again. We know the K. If you are looking for that K, we know the K and we know the thickness. The insulation material is given to us. So Jesse is saying find the resistance. Well, the resistance, I know the resistance, right? This, I have this.
So it's off of Q and then use that stuff for the switch temperature. This Q is going to be equal to that.
But we don't know the Q.
So
Convection.
I can't hear.
We do Q conduction equals Q convection.
Yes,
No,
only
that
only
makes-
only if you know the Q convection. But see, the problem now is getting Q convection. Mallory is saying if you, because we did this problem before, if you actually say that Q conduction equal to Q convection, and so in the convection side he's going to say it's T infinity minus this T that you're looking for, and on the conduction side she's going to say it's this T that you're looking for minus the tank. Right? Yes, this equation seems that it will have only one unknown, which is the temperature of the outer surface that we are looking for, except that we don't know the H convection, because the H convection depends on, according to this formula, depend on the temperature you are trying to find. So what's the way out of this?
T average.
Say that again.
The T average, temperature average.
But that's a good choice, actually. So Ibrahim is saying, you know, that outer surface is probably going to be between the 20 air and the minus 190. But it's not exactly in the middle, but it could be between them. So I guess I will add to his advice, recommendation, that this is just what he come up with right now is not really the actual temperature. It is initial guess. So this problem has to be done by trial and error. You assume what is a good temperature, and that's a good that's a good initial guess. It should be in the middle between them, right? And then once you have the temperature, you calculate the H from the outside, and then you do what Miller just did or said we should do, and you get the outer temperature, and you check, is it close enough to our assumption? Will the properties, because really we need it just to get this guy. In this formula, that's the only thing that will change with TS. So will it make the viscosity change a lot? And will this change our Nusselt number that much? If it does, then we go for another round with a better guess for the surface temperature. If it's okay, it's close enough, the viscosity will not change that much, we are done. So what does it mean we are done? We have, that temperature was good enough, and now we can get our Nusselt number. So the Nusselt number, you just put it in this equation, the Nusselt number will be 2316. And that Nusselt number was HD over K. For a cylinder, HD over K. And so that make our H 14.20 watt per meter square degree C. Right? Back again, what are we doing? We would like to calculate the Q dot so that we can get how much nitrogen will melt. We said we are going to calculate the Q dot. The Q dot was delta T over 2 resistance, convection plus conduction. We wanted the convection resistance. So we had to come with the H. Therefore, we have to use one of those so many correlation in this external heat transfer chapter. We figure it's a sphere, therefore this is the equation for a sphere. We use it, we get our Nusselt number, and therefore we get our H. Now we have this, and this, we can calculate the Q. So the Q would end up being, the Q dot is T infinity minus the T tank, sorry, over the 2 resistance, 1 over HA plus R2 minus R1 over 4 pi K R1 R2. Everything is given now. This ends up being 7433 watt. This is equal to M dot HIF, or the latent heat. This latent heat was 198 10 to power 3 joule per kilogram, and stick to SI units so that you wouldn't go wrong. And therefore M dot become 0.037 kilogram per second. Right? Question about this problem? So really, again, you know, this chapter is about getting the H from a Nusselt number relation, and then you use that H to calculate the Q. So this one is a little bit more than Q is H A delta T because you had also conduction sitting next to it. So it was conduction plus convection. And we calculated the Q, and then that Q can be used for anything, heating, melting, cooking, in different problems, right? So now for flow over a cylinder, here is the correlation, right? Almost like the other one, you know, they because they are essentially trying to transfer the fluid mechanics into heat transfer, you will always see a Reynolds number and you will always see a Prandtl number. It's just the constant will be different, the coefficient will be different, but it's exactly the same procedure. So see in this example, in the last 3 minutes we have, so in this example he said a person extend his uncovered arm in the wind and the rate of heat loss from his arm is to be determined. He would like to calculate the Q. So this is the arm of someone. And here's other arm here. And so he would like to figure out how much Q is actually leaving his arm. All right, that's a flow over a cylinder. Here is a correlation for it. What do you think the Q would be? The Q is, anyone? Can anyone help me give me the Q? How much joule per second is leaving his arm or getting to his arm, depending on whether it's hot or colder than his temperature? What's the equation? HA delta T. And the A is the area of the cylinder. So what's the area of the cylinder? Bar by dl, correct. And to get the H, what I'm going to do? By the way, the delta T here is the TS is 84 Fahrenheit, T infinity is 54. We got the delta T, right? He's being cooled by the air, so the air is colder than him. Huh? Right, we have to figure an equation for a cylinder, right? Yeah, this one. Right, this is a flow over cylinder, but now we have to check to the recipe. So the recipe say the fluid properties are evaluated. Remember at the sphere, the formula for the sphere was everything was at T infinity except for the mu s. This time he said the properties are at T film. So we basically say 54 plus 84 over 2, that's the T film. We open the table for air at T film, and we get the viscosity, the K, the Prandtl. We need the 3 of them. The viscosity will go into the Reynolds, the Prandtl is there, and the K, so that we can get the H out of it. And we are done. Make sense? Yeah. All right. Thank you.